Third. Welcome to American Association of Bangladeshi Engineers and Architects, or AABEA's expert presentation and interview session. We are very fortunate today to have Professor Dr. Saifur Rahman of Virginia Tech to talk on his, let me share the screen and go into the presentation mode. So today's topic is a portfolio of technology solutions to achieve global decarbonization. And the keynote speaker is Professor Saifur Rahman. I'm Anis Rahman, moderating this session. So as an introduction, this is basically what I collected from Professor Saifur Rahman's introduction abstract. As is known, there is an unprecedented level of awareness of climate change all over the world. The role of decarbonization in enabling environmental sustainability is the topic today that Professor Rahman is going to give us a presentation on. Main priorities for doing so is, as Professor Rahman indicated, is energy efficiency applications, carbon capture systems, renewable energy integration, hydrogen and storage solution, cross-border energy transfer, and advanced nuclear technologies. So with this, my extreme pleasure to say a few words about our distinguished speaker's bio. He's very well known in the community, not to mention that he is the president-elect of the biggest engineering organization, IEEE, or Institute of Electrical and Electronic Engineers. They have close to 500,000 members all over the world. And Professor Rahman is a life fellow of IEEE, and he's very, very well known. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. Professor Rahman has published about 140 journal papers and made over 400 conference and invited presentations. He is also an entrepreneur. He is the founder of BEM Controls, LLC, a Virginia-based software company that are providing building energy management solutions. Professor Rahman has conducted several energy efficiency, blockchain, and sensor integration projects for Duke Energy, Tokyo Electric Power Company, the U.S. National Science Foundation, the U.S. Department of Defense, the U.S. Department of Energy, and the state of Virginia. So without further ado, please welcome Professor Rahman for his distinguished presentation.
Share the screen now?
Yeah, you can share the screen now with your presentation.
Okay. All right. Okay, can you see the full screen, Anis?
Yeah.
Okay. Good afternoon, good morning, depending on where you are. You heard Dr. Anis talk about the topic today and myself, which is nice kind of him. I would focus on the issue of global decarbonization. But before I talk about decarbonization, I must tell you what is carbonization, why it's a problem, then give you solutions and the world situation where we are, how we're going to move out of this mess. So what is carbonization? This is data for last 800,000 years, global data. If you look at the numbers here on the screen, 0 is 1950, going backwards, 800,000 years. And there have been many ways people have been able to calculate these numbers. You might ask me that question, how do I know? How does anybody know what happened 800,000 years ago? How do you know? We have this, if you go to the North Pole, the ice core. The ice today was air 500,000 years ago, air. Air had moisture and air had CO2, nitrogen, oxygen. That got frozen and went down in the ice sheet. You go drill 50, 60 meters, you bring up that core of ice, and they analyze the amount of CO2 in that ice core and you carbon dating the age. That's how you know what the CO2 concentration was up to 1950. Very interesting data. If you look at the numbers now for the last 800,000 years, the level of CO2 concentration in the atmosphere never exceeded 300 parts per million, 300 ppm. That was the data. 1950 is my zero number. If I go from 50 to 2020, it has gone to 420 parts per million, from 300 to 420 parts per million. That's something we have to worry about. That is carbonization. Data came from US NASA data. This is another way of looking at it, more recent data, 1750 to year 2020. Why 1750? This is before the industrial age in Europe. That's when the steam engine was invented and they began to burn coal to make steam and run engines. The coal is the primary source of CO2 today. Look at the numbers from 1750 till about 1950 or so, 300 ppm, parts per million, atmosphere CO2. It shot up from 60 to 2020, it has gone to 420 parts per million now. That's carbonization. The resulting impact on the global amount of CO2, not just the concentration, amount of CO2. Go back 1840 or so, it's below measured values. You cannot measure it. By 1950 or 60, it's about 5-6 billion tons CO2 emissions per year. Today, it's more like 37 billion tons per year CO2 emissions. That is carbonization. And that carbonization causes temperature rise. So this is the data today. Today, 2021, a year ago, where the CO2 came from. Out of about 34 billion or so, coal was the primary contributor, 15.3 billion tons, oil 10.7, natural gas 7.5. I look at these three numbers very carefully. The amount of CO2 produced by coal per unit BTU, let's say, is higher than gas or oil. Simple number is, if you produce 1 kilowatt hour of electricity, kWh, 1 kilowatt hour of electricity from coal, you produce 1 kilogram of CO2. 1 kilowatt hour, 1 kilogram. Simple. If you produce the same electricity, 1 kWh from oil, you produce 750 grams of CO2, 3/4. Same electricity produced from natural gas, you produce half a kilogram, 500. This is, people say gas is a cleaner fuel than coal because of that reason. So I'm going to give you some answers of questions that may come up later on. Now, so that's the breakdown among three fuels. Now, where is everything else happening? We talk about global warming, climate change, carbonization. Carbon dioxide is not the only source of greenhouse gas. There's 6 greenhouse gases, 6. Number 1 is carbon dioxide. If you look at the chart on the left-hand side, if you add the two numbers, fossil fuel and forestry application, 65 plus 11 is 76% came from CO2, global warming gas. Next is methane, 16%. Methane, that's your polluting from organic waste, and of course methane from cattle. Next 6% nitrous oxide, which is from natural gas, and remaining 2% comes from different fluorine, like fluorocarbons, and so on and so forth. So 76 plus 16 plus 6 plus 2, that's 100%. That's the by gas type. If you look at the sector, where is the gas coming from? Electricity production and heat. You heat your homes in the colder countries. That gives you 25% of greenhouse gases. That's your kind of CO2, methane, and so on. Next is agriculture, forestry, and other land use, 24%. Buildings, only 6%. Transportation, 14%. Industry, 21%. Other sources, 10%. Now, what do I mean by transportation? Primarily road transport, some diesel trains, not much. If I look at global is only 14%. If you look at US, more like 34%. With global, you don't have that many trucks and cars like US, China, and so on and so forth. Keep that in mind. So electricity production is a big source, and I'll focus on that later on, why that's my field of research, electricity use and production. Get to that. Anyway, point is electricity, agriculture, transport industry are the big contributors to global warming. Now, let's come to US now. We saw globally CO2 was 76%, US 79%. Very similar number of total greenhouse gases. Methane was 16% there, 11% here, because of the number of cattle is much less in the US compared to India or New Zealand or Australia and so on, or some parts of Europe for that matter. Nitrous oxide, 7%, fluorine gases, hydrofluorocarbons, only 3%. Talk about the sources. Transportation, US 27%, globally was 14. Difference. Electric power is number 2, not number 1, 25. Industry, 24%. Residential, commercial use, mainly heating and cooling of buildings and electricity usage. Agriculture is farming, food processing, and so on, 11%. That's the US situation now. So that was where is the source of carbonization. Now, what is the impact of carbonization? What is the value chain that is suffering or will suffer due to high level of carbon in the atmosphere? Okay, fine. Look at this number. Temperature rise globally since 1850, year on year. There are 1, 2, 3, 4, 5, 4 sources of data, and they're very, very closely tracking each other. So you see some oscillations year on year as possible because of the weather conditions change, El Nino effect has impacts and so on. But trend is beginning 1975 or so, there's a very clear upward trend. To the point by 2020 or 2021 now, the global temperature has changed by 1.2 degrees centigrade from what it was 150 years ago, 1.2. The Paris debate 6 years ago now, 7 years ago, the world has agreed to keep the temperature rise to below 1.5 degrees C. That may not be possible. So what I'm saying at the bottom of my screen, the temperature goes over 1.5 to 2 degrees centigrade, then we are giving up. Point no return. It'll just explode and you'll see more damage than you have seen up to now. Point is, it is very serious. We should all work hard to keep the temperature rise at or below 1.5 degrees C. It goes over 1.5, over 2, then game is over. That's as simple as that. It may be on not my lifetime, but your lifetime, maybe your children's lifetime. It'll happen. Now, what can we do? Again, as I said, I'm not solving the global problem. I cannot. I'm focusing on electric power sector. That's my field of area, that 24% number you saw. What we can do as electrical engineers, power engineers globally, to keep our part of the challenge under control, which is power generation, power usage, power distribution. That's my focus. Okay, now this is another impact. This is a real picture. As the glaciers are breaking down, as the ice sheets are breaking down, these polar bears are stuck. They can swim to the next ice sheet. But what do they eat? Maybe some fish, possibly, and survive for some time, but not very long. That's polar bear. That's close to home, Pakistan. Flooding happening as we speak in Pakistan. 34 million people have lost their homes. 34 million people. People are outside their homes. You can see the pictures here. The water level is above the first floor roof level. This is in Sindh province. People walking knee-deep or waist-deep water to get out the flooded zones. And right-hand side, same thing. This is the impact of high carbon dioxide in the area people live in. The people are all over the world. Now, you have to remember, the CO2 we produce in Virginia goes to the sky, and the sky also CO2 produced in Beijing or New Delhi or Bangladesh or Pakistan, all in the sky. So it doesn't matter who makes it, so all gets there and stays there. And CO2 lives in the sky for 150 years, not just few years. There's anything that Germany did, the UK did in 1850 is still there. And that's the challenge. I'll come back to that in a few minutes. Which country should take more responsibility going forward? It's a challenging question. So let's keep looking. Now, let's come to the more recent time. I want to show we are talking about it for many years, but not making much progress. I remember Queen Elizabeth, who died yesterday, was in Glasgow 2021 UN Convention on Climate Change. She was asked this question: what do you think will happen in Glasgow in the COP26 conference with global leaders coming here? She said, I remember it clearly in BBC, these guys only talk. They don't do anything. Queen said that, they only talk. So this is an example of nothing happening. 2015, 16, 19, same. Global emissions, 76%, 75%, didn't change, CO2. Methane, 16%, 17%, no change. Nitrous oxide, 6%, 5%, no change. Point is, we've been talking for the last 10, 15 years about need to do something, and we come on, the leaders come in, talking late night discussions, they write a portfolio and a report and go home and forget about it. They come back again next year. In fact, the climate change convention happening in Egypt in a couple of months from now, in November. And I'll be there and talk about this issue there. So we'll see what we come up this way. My point is, I'm not going to disappoint you. I'm a realist. I am telling you what has happened. So you, as a citizen or a student or a professor or a homeowner or an engineer or a doctor, whatever, tell your political leaders, do something, please, because it is a serious effort that we have to take into. Now, who is more responsible? Recent data, 2000 to 2021. On the left-hand side is emerging economies. China, number one. China in 21 produced 12 billion tons of CO2. 1 year, 2021. India, next one, about 2.7 billion tons of CO2. Advanced economies, EU, Japan, and US on the right-hand side. US is the highest, 6, coming down to more like 4.5 right now. And Japan was flat, and EU has gone down some. This is the debate, and come back to that again later on. China said, yes, we are producing 12 billion because we are developing. The US cannot complain because US and UK and European Union, if you go back 100 years, you produce a lot when China was kind of agricultural country. India, same thing. This is the challenge we have to accept and move on. Now, I'm getting my focus now. I'm showing you now not that 32 billion tons of CO2, CO2 coming from electricity and heat production for heating homes, heating factories. Very focused now. That's about 14 billion ton out of 32. Heat, electricity. Big chunk is coal, the brown one, 25%. And then natural gas, then oil. And then the top is, this is waste that is not recycled. Like you go to garbage, the organic waste from kitchen waste, that's being used today in some countries, US included, to produce electricity. So it's a very small number. Point is, coal is a big chunk, natural gas and oil. That's the 3 bars. Then you got 2 lines, green and yellow. What is this? This is the share of generation, power generation, heat generation from these 2 sources. Coal was about 38% in 2000, became 42, 43 in 2015. Now it is about 36%. That means coal is used for electricity and heat production, and CO2 emission from coal is 35% today. Oil, low emission, not oil, low emission meaning nuclear, hydro, solar and wind, low emission. These are slowly growing. Between them two, about 70% or so. The rest are from other transportation and factories, all that. Just keep in mind where the problem is coming from. Now, that was electricity, power. Now look at transport sector. Very recent data, January 20 to January 21, just 12 months. See, 4 or 5 lines. At the bottom, the blue one, aviation. All these numbers are negative. Why negative? Because of the COVID situation last 2 years, we flew less. So aviation industry used 18 million tons less CO2 than they did in January 2020, because spring of 2020 was very high. COVID situation, many things did not move. That's aviation. Public transport, not much. Big chunk is surface transport. People didn't drive to work. Buses were shut down in the US at least. Big change. Then industry, again, they're shut down. Production was halted. And power sector, you just talked about some. So big chunk was surface transport does not function as much as we are used to, drop it. Then they're coming back now. Point is, it can be done. We didn't die because of we didn't drive or didn't go to work or didn't fly. We didn't die. So we have to understand it is possible, but we have to have the political will and the power to control our emission. Now, that's global. Let's come to US. On the left-hand side, what are the sources of energy that are used in the US? Petroleum, mainly transport sector, 36%. Next, natural gas, mainly electricity production in the US. Non-fossil, that's your renewables, nuclear, and the like, coal 11%. 11% only coal in the US for energy consumption. That was consumption. Now, CO2 on the right-hand side. What is the biggest source of CO2 in the US? Biggest is 46% from petroleum. Why? Transport sector. Big source. We understand this. In the case of power sector, which is coal and natural gas, about 55% together. So these are the 2 big ones in the US. Again, we have to look at power sector. That's my focus as we go forward. Now, a little bit of complex data here, but I'm going to show it to you. You are asking the question, what's the breakdown? On the left-hand side, for the over 5 billion metric tons of CO2 that US produced in 2021, let's say, 46% came from petroleum, gas 34%, coal 21%. We've seen that before. I'm breaking down on the other side, what is the sector, not the fuel source now. Transport sector is highest, 37, industry 28, residential 19, commercial 16. So you are a homeowner, you're living in a dorm, you're working in an office building. So think about what you can do, reduce electrical demand or heating demand in your building where you work or live. This is very interesting data. This is the debate between the developed world and the developing world. If I go back from now to 150 years back, 1870 timeframe, who did what? 23 rich developed countries were responsible for half of the global CO2 emissions up to now. half of it came from 23 countries. Other half came from 150 countries. 23 produced half, other 150 produced remaining half. Breakdown, US was a big chunk, 24.6%. Today's emission total, 24.6% came from US. Quarter of it, all of it. Germany 5.5, France 2.3, Japan 3.9, Canada 2.0, small numbers, 1% and so on. On the right-hand side, the 150 countries who gave the other half of CO2, China is a big chunk, 14%, India 3.2, Ukraine 1.8, transport, global transport 2.5, Russia 6.8, the big ones. Others are 1% or less. This is the data we face in debates. People come in, India, China, Indonesia, Vietnam, Pakistan, Bangladesh, said, well, you are blaming us for producing so much CO2 now, but you produced so much the last 150 years, so something has to be done. So my approach is, as the IEEE president, I don't want to fight. I want to give a solution that both parties can live on or live with. That's what I'm talking about in the next 15 minutes or so. Now, so again, similar data. 12% of the global population is responsible for half the global CO2 emission. 12%, 50%. Remaining 88% of the population produced only 48%, the rest 2% from flying. There's nobody's focus is not. You go from Washington to Paris, you burn, the plane burns fuel. Whom do you count for Paris? Count for Washington. So you don't count for anybody. It's a global number. Fly from Washington to, I don't know, Brazil, same thing. So keep that in mind because these data are important because we have to understand where the problem is before we can give solutions. Good. Now move on. So this is something I'm focusing to my field of interest. As Dr. Anis said in the beginning, there is an unprecedented level of awareness about climate change, which is good. People like you and me asking these questions. We did not ask these questions 20 years ago. And we need to have an environment that is sustainable. Fine. Therefore, in my case, I am putting major focus on the carbon produced through power generation because it is responsible for, as you saw data, for 30% or so of the emissions globally. So this is where we have to start. Again, my field, I'm not solving the global problem. I cannot. I can talk about what I know. Okay, this is the debate and the tension we just briefly spoke about. The tension between industrialized nations and emerging economies for the decarbonization, I believe, requires a portfolio of solutions, low carbon generation, storage, demand side management with technology and focusing on energy efficiency. Very simple. If you use less electricity in your building to get the same thing you do, you're using less coal to produce that electricity. Very simple. So this is the cheapest and fastest way to decarbonize. Use less. We can't do that. Example today, California. Because of power shortage, the authority is telling us, please raise the thermostat to 78. It was 72 before. I keep 80 degrees myself at home. 72 is too cold. I go to grocery this morning, it's cold in the grocery store. It's hot outside. Why keep it so cool? This is the culture. That has to change. Possible. So I'm saying in order to address the global warming carbon fuel usage challenge, let's focus on what we can do as individuals, which is use less electricity, but don't sacrifice your quality of life. Keep that in mind. Now, these are my 6 proposed solutions. Dr. Anis showed that once already. First, use less electricity or less energy by energy efficiency applications. Give examples in a few minutes. That's one. We cannot shut down all the coal plants in the world today, not even next 20 years. Not possible. What I'm saying, you will have to build, not preferred, but you have no choice. India, China are very good examples of that. But please build highly efficient power plants so that you use less coal to produce same electricity. And the carbon you produce can be captured and stored, so it doesn't go into the sky. Number 3, promote and deploy more renewables, solar, wind, hydro. Promote, not only promote, deploy, use it. 4, use hydrogen and other storage technologies to make renewable energy more useful. Why is that important? Typically, sunshine happens during daytime, you need power at night. You need to store that energy. Data shows in the US at least, wind is more prevalent in this nighttime than daytime. To use that wind is in excess, you cannot use it, you let it go unused. Don't do that, store that wind power in some storage device, hydrogen, battery, whatever it is, and do that. Example, Denmark and Norway. Denmark has more wind power at night than they can use it in their country. Storage is not there yet in large scale. What do? They send the extra power from wind energy in Denmark to Norway at night. Norway has been using mostly hydro for their power generation. What Norway does, they hold the hydro back a little bit, use the low-cost Danish electricity at night. The water they held back is available for use following daytime. The Danish wind is not as strong at night, demand is high. The Denmark imports hydropower from Norway at daytime. That's a good example of not only cross-border power transfer, but storage. Storage doesn't mean store in battery only, store in water storage. That's what Norway is doing today. That's what I mean by, and what is hydrogen? Hydrogen is not a primary fuel to make it from something. So you break down natural gas to make hydrogen or break down water to electricity. So if you have excess power at night, use excess electricity to produce hydrogen. Number 5, explore cross-border power transfer with neighboring countries. I just mentioned Norway and Denmark. US, Canada does a lot of transfer also. US, Mexico does some. Europe, extensive. The French nuclear power goes to Italy during the afternoon and to Switzerland as well. This is happening. And finally, this is, some people would not, may not know this, we have globally in a image problem with nuclear because of Chernobyl, because of Fukushima, and so on. So those are big reactors, 1,200 megawatt each. Now there are new technologies which are small reactors called small modular reactors, SMR, which are small in capacity, so they can be managed and not as risky and not accident prone. Let's look at some things we've talked so far. First is energy efficiency. That's my field of research. I have done research, I have data that shows if I raise the temperature in my building by only 2 degrees Fahrenheit, I can save 15-20% energy over the whole year, especially in the summertime. 2%, a 2-degree rise saves you energy 20%. Lighting even more. If you dim your lights, turn lights off when you don't need them, you can save, again, data from Virginia, about 25%. So that's a big number. 20%, 25% means you use less fuel, less coal, less oil to make that electricity. In addition to energy savings, I think we are missing out on something. In many offices, it's too much light. Stores too much light. It's too cold, I said. Grocery store I went in this morning, too cold. So you are not only saving electricity by reducing the light intensity or changing the temperature setting, making their place more comfortable. So this is what I have to point out. I have visitors from India, Bangladesh, China. They come to here in Chicago, Washington, they go shopping. It's too cold for them. So they said, why is it? Well, this is the culture. Anyway, I just mentioned this briefly. Use more efficient light bulbs so that you're using less electricity. Example, bullet number 2. If you use LED light bulb, uses 15% of what is needed for an incandescent light bulb on the right-hand side of the screen. Same light, 100-watt incandescent, give you some light. 15-watt LED, give you the same light. 15-watt, 15%. If you change your light bulbs from incandescent or CFL to LED, you save a lot of electricity. So what we are saying, we would encourage the developed countries to help developing countries to reduce electrical demand from lighting by giving them a technology or giving them money to buy these bulbs. This is the issue. This is my solution. Let's work together, not blame each other for the problem that we are facing. That was number two, efficiency issues. Number one. Number two is highly efficient power plants. The two kinds of power plants are available globally that are more efficient than traditional power plants. One is called combined cycle gas steam power plant. I'll give an example in a second. Second is ultra supercritical steam power plant. Even Bangladesh is building one today. Ultra supercritical power plant in southern part of the country. Example. This is what is meant by combined cycle. If you see on the upper left-hand side, gas or oil fuel coming in, combustion chamber. It's a gas turbine, by the way. No steam, no water. And the gas turbine runs, and the exhaust gas, as it leaves the gas turbine, is used to heat some water. It's called heat recovery steam generator. The blue water coming in gets hot, and the red or brown water goes to steam turbine. That means the heat being used in the steam turbine is not coming from a coal plant. Is the heat that you extracted from the outgoing gas exhaust from the turbine. If you didn't extract it, it'll go out in the sky. That's one example. Second example is ultra supercritical power plant. I'm on the same picture now. Sorry, this is still the combined cycle. This is a 560 megawatt combined cycle unit in Louisiana in the US. Cost $700 million roughly. This is highly efficient. Second example is coal-fired ultra supercritical power plant. I'm not going to go the details here just to see why you call it ultra supercritical. If you look on the top left-hand side, the main steam cycle is coming from steam, of course, but then you're using another heat source. The sign of fire here, another heat source to make the air, which is going to heat your steam generator, heat hotter. And the rest is details about pumping and condenser and all the other stuff. So again, is extra heat source to make the plant more efficient. It's called supercritical heat. Example is this one. Plant in the Netherlands. 800 megawatt each rated, efficiency 46%. Those of you who do not know, typically a coal plant is 40% efficient, 40% or 42%. You raise to 46%, that means 10% more. The 10% more efficient means to get same electricity, you use 10% less coal, as simple as that. And 10% of million tons of coal is a big number. And the heat temperature is 609 degrees centigrade, as an example. So this is it. Now the third item, carbon capture, we just talked about. What is carbon capture? Typically, when you burn coal, you have a chimney, right? The CO2 goes out the chimney into the sky. Rather than let the chimney release the CO2 into the sky, you will extract that CO2 by chemical means or other means and hold it and push it into the ground. Typically, old coal mines, old salt mines and the like. They're stored there for as long as you can. That's called carbon capture and storage systems. So if you cannot forget coal, which you cannot, do two things: use more efficient coal plants, or use combined cycle gas plants, or try to extract the CO2 from the air and hold it somewhere. That's called CCS. Again, a plant in the US, a carbon capture plant. So my point is, this is not just theories happening today, but not in large scale enough. Second, next is renewable energy integration. We have solar, wind, and hydro. Look at three things: production, transmission, distribution. Why is it important? When I produce electricity from a coal plant, they're 100 miles from my city where I live, 100 miles or more, in fact. That coal generated power has to be brought in over transmission lines. If I use rooftop solar on my building, I don't need a transmission line. No infrastructure needed, as much as I can. Same distribution. So look at the countries which are big on solar and wind today. Top 10 countries, China number one. This is data from 2018. 700,000 megawatt came from non-fossil, non-nuclear sources in China in 2018. US number two, about 250 gigawatt. Brazil three. Why Brazil comes up? A lot of hydro in Brazil. Germany, a lot of solar, and so on. India number 5 here. When I talk about renewable, what I'm talking about on the right-hand side, about half, 48% is hydro, renewable hydro, 23% onshore wind, and 20% or so solar photovoltaics. The rest are solid fuel, meaning wood. This is the global breakdown. Next item on my list of 6 is hydrogen and storage solutions. We have to find a way to use energy at night, which is going unused in many cases. And one way to do that is make hydrogen from electricity so that that can be stored and used next day for other applications. Cost is lower. So again, do not let the electricity go to waste at night. Cross-border energy or power transfer. Since we are in this fight together, let's find ways to share each other's excess production and excess demand. If you remain within your borders, every country, in fact, by the way, globally, almost no country is self-sufficient in anything. You buy something and sell something. So electricity, in the case of US, a big country, buys a lot from Canada. Canada buys some from emergency purposes. Same with Mexico. And of course, Europe is a big example. France started Spain, France, Germany, Austria, then on to Greece and in Italy, all sharing power. So that has to be done carefully. Finally, advanced nuclear technologies. Small modular reactors can play a big role because they are slow. I mean, slow in the sense they're not going to explode like big ones can. And they're small because you don't have to build a big one upfront. In many cases, when you build a nuclear power plant, in case of Bangladesh, for example, is 1,200 megawatt times 2, 2,400. Those are big chunks from the capacity. If I could build them in chunks of 100 or 50, I can plan ahead better. And that's what I'm going to show you in the next picture here. That's a small modular reactor example. Look at the size, only 20 meter tall, 2.7 meter diameter, weight is 590 tons. Whole thing, 600 tons. In a nuclear power plant, 1,000 megawatt or higher, the building that contains nuclear fuel itself costs like more than 1,000 tons. One reactor vessel, 1,000 tons. Here, the whole plant is under 600 tons. And 50 megawatt, 60 megawatt, what can be done? You get one, drill a hole in the ground and put in the ground and forget about it. It's done. Everything is done internally, much less risky. So where are we heading? If I start on the right-hand side of my screen, right to left, this is from the case of one company in the US, a Southern company, their plan. 2007 was the baseline. by 2017, they reduced their CO2 emission by 36% from baseline, 2017. 2020, they have gone to, that was target, didn't happen. But what they want to see, by 2030, they get half of their energy from non-fossil sources. And by 2050, net zero, meaning they would not produce a net CO2 on an annual basis. And one company. By the way, Europe has promised 2040 net zero emissions, US 2050, China 2060, net zero emissions targets. Okay, so the bottom line. We are trying to replace fossil fuel with nuclear and renewables happening. But the risk is transport sector. Unless we electrify, we'll be using more and more gas and oil. You saw the numbers go more than 42% of 40% in some cases, will not be enough to make up for the savings we are producing from power sector. Transport sector will eat it up. So large-scale EV deployment would be a solution, but the question remains, electric vehicle requires electricity. Where's that coming from? If that's coming from coal, it doesn't help you. So make sure you not only talk about electric vehicles, talk about what is the fuel you have to use to make the electric vehicle really benign. That's it for now, Anis. I gave you here my email address, s.rahman@org, also my website, srahman.org, my own website. I put all my lectures on my website when it is done. So those of you who have no access to this slide deck, go to my website, maybe tonight, and get whole deck is there. And you'll see my other 30 talks I have given in the last year or so. That's it for now. Stop sharing now and go back to you running the show, Anis.
Well, thank you very much, Professor Saifur Rahman, for the enlightening lecture. And this is a huge problem. And you gave very, very reasonable solutions if only we can implement. By no means I'm an expert in this area, but I have some curiosity. For example, the nuclear. The bigger nuclear reactors has the age-old problem of recycling the fuel, spent fuel. Will that be solved by the small modular ones?
Yes and no. There are many different technologies being used for SMR today. One is steam cycle, like large power plants. One is gas reactors. South Africa has designed like this. If the gas cooled, then is not issue of replacing as much fuel per year. But why it is an issue with spent fuel? A typical nuclear reactor must be refueled every 18 months. The 1/3 of the core comes out, no place to go. They go to a swimming pool near the power plant and stays there forever almost right now. That's today. If you enrich the fuel to more than 5%, it's 5% limit today because security issues, 10%, then you have to reduce the frequency of refueling, right? 5% every 18 months, 10% every 3 years. Less refueling means less spent fuel to be dealt with. There's a problem with that. Why 5%? If it goes over 10%, it becomes nuclear bomb-grade materials. And that's much higher, but this is a starting point. That's a big deal with Iran and the West right now on that very topic. So they're saying, why is the proliferation at risk? Somebody can attack the nuclear plant and steal the fuel rods. To put them in the ground is not easy to do. The stealing part I'm talking about. So you can enrich them higher level and not worry about the fuel rod being hijacked and taken by somebody. So that's a political decision and science part of it. So answer is, yes, nuclear Small ones would not solve the problem 100%, but it'll slow down the growth of the problem.
Right. All right. So, excuse me. Well, one other thing is the solar energy and wind energy, as well as the hydro energy, which is very feasible probably for Bangladesh and countries like that. But so one at a time, the solar energy, um, I unless we industrialize and a technology, it's very difficult to reach to the people. So, for example, we have automotive industry. We can buy, use it, change it, etc. And is it possible for solar energy to become a sustainable industry without government subsidy and help, especially countries like Bangladesh and African countries and that kind of developing countries?
Well, it depends on which way you're looking from. I have seen in China, for example, now that solar makes a lot of sense without the government subsidy because prices come down significantly. And also, it's an issue of relativity. What is your cost of electricity where you are right now? If you go to Hawaii today, Honolulu, solar is cheaper than electricity from power plant because of all oil and gas based in Hawaii. No nuclear, no coal, nothing, no hydro. So it is a case-by-case situation. Without government subsidy, it's difficult because as you go to poorer countries, they don't have a lot of capital, a lot of cash to buy or borrow from bank. So that's difficult. Bangladesh had a program which is slowing down now called Solar Home Systems. Bangladesh has deployed more than 5 million such systems in the last 15 years or so, highest in the world, through bank loans. It's possible, and some government subsidy. So it has a mixture of bank loan, government subsidy, and biggest is awareness that it is there. For example, in the US, where I live in Virginia, Maryland area, is a backlog of rooftop solar projects. They figured out cheaper and better, the backlog. That means it's a good sign. And there's some government subsidy, but not a whole lot. So government subsidy, awareness, availability of equipment, technical force, all of that have to come together.
Right. So, the one of the issue about solar is as you have just mentioned, availability. The solar panels come from sand. Sands are processed and silicon substrates are then made the circuit, etc., etc. Now, is it feasible for Bangladesh to get into producing the base material, which is the substrate for solar panels, and that way, because availability problem could be solved that way. But again, if everything depends on the government, it's very difficult to make progress. On the other hand, the private sector is not ready to take the risk of not making benefit for a few years, because they have a learning curve there to make the panels themselves. Any suggestion to solve this problem?
It's a common understanding, which is not 100% correct. It's true that silicon is the base material for crystalline solar cells. True. We call them silicon solar cells for that reason. They call silicon cell. But silicon can come from ash, can come from rice hulk, come from sand. Right. The problem is the refining is very expensive, very, very expensive, and takes a lot of electricity to refine it.
Right.
That is why you can buy Vietnamese panel, Cambodian panel, Malaysian panel, all cells come from China. China is a huge infrastructure to make solar cell silicon. So it's an issue of industrial depth, manpower, and low-cost electricity, and government investment. So Bangladesh, to be honest with you, is not possible because you have to invest a lot of money and then compete with China to sell to other countries. Because if you build industry so large to be profitable, you will produce so much solar cell that you can use in your country. It is exported. That's the challenge.
There's obviously a big challenge for sure. And also one other thing is recycling the solar cells I mean, how are they doing today? And what the impetus of this question is that China is supplying some 80% of the polysilicon today all over the world.
Correct.
And developing countries and the United States have interest to bring other countries as part of the supply chain.
Right.
They are doing a lot to help countries like Vietnam, Philippines, Malaysia, and all those countries over there. And Bangladesh couldn't be a big source. I mean, if there could be a source of some sort other than the garments alone, then, and of course some tea and jute and fish, etc. But in the technology side, so what can we in the sense the experts like you and others, can any recommendation be made to the Bangladesh government or stakeholders? I don't know who they are. They should look into this opportunity because it's an opportunity. The supply chain opportunity is there, and they should be able to capture the slack or opportunity that is there. How would they be able to do that? And is there an avenue to make any suggestion to them that they can implement? I mean, there are a lot of suggestions going to them, and they bypass a lot of them.
Well, good example is the garment industry in Bangladesh. You go back 25, 30 years ago, it was very small, very small.
Right.
And somebody figured out to do this, and they were successful. Now it's a full chain from cotton to thread to cloth, fabric to the finished product in Bangladesh. The full scale. It has happened. Can that be done in the solar sector? On paper, yes. Two questions remain. Garment requires electricity, of course, but solar requires much more intense because there's a process issue. So Rahim Afroz has a plant in Bangladesh. They make solar panels using imported solar cells. That has not taken off. I don't know why. Maybe government didn't get enough incentives for doing this. And maybe garment, there was a market in Europe and US because of the price differential. So, and Bangladesh was early on, had not much competition in that field. China was competing, China's price went up quickly, and then China still number one, but still pulled back quite a bit. You mentioned Vietnam, Thailand, Cambodia, Philippines, Malaysia, all that. That's true. They have that. So I have to carefully study whether Bangladesh can make enough at a low enough cost to compete with them, because they have a channel set up. They sell to US, by the way. US buys from all those four countries today. So Bangladesh has to enter this market. They displace somebody else. My solution would be halfway there, not all the way. Talk to Malaysians or talk to Thailand maybe, that if they can open a branch factory in Bangladesh of their supply line, because of lower labor cost.
Right.
Unlike garment industry, solar sector cost of labor is much smaller percentage, much smaller, 5% or less. That's a big difference by saying my labor is cheaper. You can give low cost electricity, a low cost land, low cost and more synchronized business process, a big deal. That is a possibility.
Okay, so one other quick question about the recycling. Even in the United States and other countries, Japan, who are using solar cells a lot, the used ones become they have to put it in trash or something. I don't know how they recycle it.
That's a big question globally. I'm taking part in a debate in Maryland, in fact, on this very topic. What is to do with the end-of-life solar panels? I have a solution. People have not bought into that yet. Nowadays, these are fairly big panels, 1 by 1.5 by 2.5 meters, pretty big size.
Right.
And they are very strong by design.
Mm-hmm.
And they are almost, they're very strong in the sense, if you have hailstorm, won't damage them. Solar panels are covered by glass. And by design, it has to pass certification. You drop a 1-inch diameter steel ball, 1 meter height, glass cannot break.
Right.
That's the design. It cannot break. That means they're very strong. And the glass sealed. So I've told my friends here, when you are done with the solar panels, send them to Africa. They use them as roofs, as opposed to tin shed. That's a roofing material. And that could be one way of taking, and then it can last forever. Meaning, glass doesn't break. Glass doesn't rot, like tin rots. Glass doesn't rot. And aluminum frame. So that's also rust-free. That's really my solution. Collect them, ship them to Africa or other countries globally, and let them use it for roofing material.
And one other thing is, it's a kind of a science fiction solution people have been, I saw somewhere that now that we can go to the outer space,
right?
Why not harvest energy from some sun, put the solar panel all around it, cover them, and the energy generated transferred to the earth. So how will, even if the science fiction ever comes true, how will they bring the energy to the earth? That problem has not been solved. Any suggestion for them?
No, this is not science fiction. This is fact. I was looking at that in NSF 30 years ago. It's called satellite power system. That's called. NASA has a program on this. It's been coming back again now. Why? How does it work? They say we'll put solar panels on the moon. On the moon.
Mm-hmm.
Moon has no cloud, no rain.
Right.
You're facing the sun all the time, depending on which way you're looking from. And then beam that power in a microwave form from the moon to Texas or someplace, or Florida maybe. Microwave.
Right.
First of all, you have an antenna on that side, convert AC power to DC power to microwave. Microwave flows through the atmosphere, comes to Houston at the Space Center, and then you put an antenna to convert the microwave to electricity. Done. Problem is very simple problem, very serious, simple problem. That is the beam that's coming through. Unknown caller. If you have a airplane flying through that, it will be fried. Literally, a microwave oven, fried.
Right.
Birds would fry. So they're trying to figure out how to reduce the intensity of the microwave beam. You make that antenna bigger, you have less intensity by definition, wider, but then in more space to hold it. And then that's subject to wind and storm and hurricane. So this is a physics challenge now. Engineering challenge, not a science fiction issue.
So I think then maybe entrepreneurs like Elon Musk or Jeff Bezos, they should at least initiate, and then it will go in its own way probably down the road.
No, it's a possibility. But I fly a lot. When I go over Russia, parts of China, so much free land there, so much land, and also North Africa, so much free land.
Right.
So don't go to moon, go there and build a transmission line. That's it.
First, do this one.
Cross-border power transfer is my solution, not moon or whatever it is they want to go do that.
Wow, wonderful. Again, I wish we could continue this a little bit longer. And I know you have many other expertise and topics to talk about. Maybe down the road we can do another one when you have some time. in between your busy schedule. So with that, on behalf of AABEA, I really thank you very much for your time and expertise.
Thank you, Anis, for your encouragement, patience, and interest in what I have to do or what I have done today.
Thank you.
Thank you. Thank you. Take care. Bye-bye.